Imagine walking into your kitchen. You press a single button and a full roast dinner appears in front of you. No farms, no factories, no supply chains, no cooking. Just energy turned into matter. In Star Trek, this is normal. But here's the real question. Is building a real Star Trek replicator possible? In this episode, we're going to break down the real science behind Star Trek replicators, and whether we could ever really build one. Welcome to the Real Science of Sci-Fi. In shows like Star Trek The Next Generation, replicators can produce food, clothes, spare parts, medical supplies, even complex tools. In Star Trek, they explain this by saying that replicators can convert energy directly into matter using advanced matter-energy conversion, the same technology derived from transporter systems. That idea fundamentally comes from one of the most famous equations in history, E=mc². Energy equals the mass times the speed of light squared. Energy is effectively interchangeable with matter. That's what Einstein told us. So in theory, if you had enough energy, you could create matter from nothing. So let's do the maths. Suppose we want to replicate 1 kilogram of food. According to Einstein's equation, that would equal 9 times 10 to the 16 joules of energy. That means you would need 90 quadrillion joules. For comparison, the atomic bomb, dropped in World War II, only released around 6 times 10 to the 13 joules. A large nuclear power station produces around 3 times 16 joules per year. So to replicate a single kilogram of food from pure energy, you would need more energy than a nuclear weapon releases. Every meal would be a controlled nuclear scale event. So a replicator wouldn't be a handy kitchen appliance, it would be a strategic weapons platform. So unless your starship runs on antimatter reactors, pure energy to matter replication is wildly impractical. But maybe replicators don't create matter from energy at all. What if replicators don't create matter? What if they just rearrange it? Instead of turning raw energy into atoms from scratch, you could just store raw feedstock. Bit of carbon, bit of hydrogen, bit of oxygen, nitrogen, some trace elements. Then you rearrange those atoms into food molecules. That's far more plausible. We already manipulate atoms today. Scanning tunneling microscopes can move individual atoms. 3D bioprinters can layer living tissue. Automated chemistry systems can synthesize complex compounds. So instead of a magical energy converter, a replicator might actually be a very advanced molecular 3D printer. That sounds much more achievable. But then we hit the next problem, and unfortunately it's even bigger than the energy issue. To replicate something, you have to know exactly what you're building. Let's take a steak. It's not just protein, it's millions of muscle fibers, complex fat distribution, folded proteins, water molecules, trace minerals, aromatic compounds. Every molecule has a specific position. A single human cell contains roughly 10 to the 14 atoms. To store the full structural blueprint of a complex biological material, the data requirements would be astronomical. You would need molecular resolution scanning and storage. And that means quantum scale resolution, exabyte or even zettabyte data capacity, real-time atomic precision manufacturing. We're not just talking about a better 3D printer, we're talking about computing and data storage beyond anything that exists today. And then there's the thermodynamics. The second law of thermodynamics says entropy, or chaos, always increases. Creating a structured object from random atoms is decreasing the local entropy significantly. So that requires energy. More importantly, it produces a lot of waste heat. A replicator assembling matter atom by atom would generate an enormous amount of thermal energy. If you tried to replicate meals repeatedly inside a small enclosed space like a kitchen, you need a serious cooling infrastructure. Otherwise, your kitchen would just become a furnace. The starships in Star Trek conveniently ignore this, but in reality, heat management alone would be a massive engineering challenge. So, what other questions are there? The first that comes to my mind is, could a replicator create a new human? If it can create a steak, could it create a person? In theory, if you had the complete atomic blueprint of a human body and sufficient energy and matter feedstock, then yes. Physics does not forbid rearranging atoms into biological structures. But practically, you would need a complete molecular map of a human being. You'd need every synaptic connection in the brain, every protein state, every quantum interaction that affects neural firing. And that's not just biology, that's identity. Would that replicated person be you or a copy? And this isn't just engineering anymore, it becomes a little bit of philosophy. But it does show potentially how replicators could blur the line between manufacturing and creation. Let's step away from humans for a moment. Imagine replicators could produce other things, such as gold, rare earth metals, pharmaceuticals, electronics. What happens then? Well, scarcity disappears for a start. Entire economic systems collapse. If anyone can just press a button and produce gold out of thin air, then gold becomes worthless. Replicators wouldn't just change kitchens, they would destroy global supply chains. Energy would become the only true currency. And that might be why, in Star Trek lore, money largely disappears in the Star Trek universe. When matter is no longer scarce, then economics would fundamentally change. Maybe that's the most realistic part of the whole replicator concept. So Star Trek isn't alone. Replicator-style technology appears across several different sci-fis. But here's the interesting part. Most of them quietly avoid the pure energy-to-matter conversion. And that tells us something. In the Orville, food synthesizers look almost identical to Star Trek replicators. But the explanation is different. It's implied that they rearrange stored matter rather than creating it from energy. That tiny narrative tweak makes an enormous difference. Rearranging atoms is hard. Creating them from energy is absurdly expensive. The Orville subtly makes the tech much more plausible without really changing how it looks. If we look at The Expanse, that takes a more grounded approach. There they have food printers, advanced recyclers, auto docks, but no magical matter creation. Everything is based on closed-loop recycling, chemical synthesis, resource management. Nothing appears from nowhere. Mass is conserved, energy is finite, and the thermodynamics still apply. If we were to build early replicator systems in the next few centuries, they would probably look far more like The Expanse than Star Trek. Let's look at The Fifth Element as well. There, a small sample grows into a full roast chicken. That's not energy conversion, it's rapid cellular growth, which actually introduces a whole different scientific issue. Where does the additional mass come from? To grow biomass, you need carbon, nitrogen, water, energy. You can't grow a whole chicken from a crumb unless you're importing matter from somewhere else. The film unfortunately skips that part. So what is actually possible? Let's summarise realistically. Energy to matter conversion, technically allowed by physics, but practically catastrophic in energy cost. Molecular rearrangement using stored atoms, much more plausible. Advanced nanomanufacturing, we're already doing it in a very primitive form. The most likely future version of a replicator would be something along these lines. It would probably involve a large atomic feedstock reservoir, AI-controlled chemical synthesis, molecular assembly at extreme precision, massive power input, heavy cooling system, but not a glowing wall panel in your bedroom, more like an industrial-scale atomic factory. But give it centuries, and that atomic factory might be scaled down. The first real replicators probably won't make tea, they'll probably make personalised medicine, on-demand organs, or emergency food in space missions. Here's the question I still ask myself. If replicators became real tomorrow, what would I create first? Money? Gold? Food? Medicine? Or something more interesting? I'm Dr. Dan Stokes, and if you enjoy breaking down the real science behind science fiction, then please subscribe to the Real Science of Sci-Fi, and I'll see you next time.